Consider this specific case here. So let's say the region is a polygon. So in the polygon, in many people's intuition here, so it's a polygon. That means it's made of a lot of vertices, and also the edges, which is the straight line segments that's joining those vertices. So here is an example of the polygon. So we have vertices v1, v2, v3, v4 to v10, and the boundaries of this polygon is just the line segments joining these vertices. And we are assuming that the way, like the order is joining these vertices, follow the orientation we want, which is after you join those vertices, the orientation of the curve means that the region is on the left-hand side, and the boundary, the edge is on the right-hand side, as in this example here. Okay, so let's call these edges L1, L2, L3, and so on and so forth. And then we know from above that the area of D is just the integral of x along this boundary. So the area of D is the integral of this, and that's equal to, so we know that this curve is composed of these n line segments. So that's the same as taking the sum of the integral along these n segments. So each Li is one edge. So you take integral of x along this edge, on L1, and then on L2, and then on L3, and then on L4, and so on and so forth. So you kind of break the problem of computing the area of D to computing the line integral along each segment of the polygon, each edge of the polygon. And then you can check that for any straight segment from x1, y1 to x2, y2, what we have is this formula here. So integral of x along L is the mean of x1 and x2 times the difference between y1 and y2. So x1 plus x2 over 2 times y2 minus y1. And then substituting this formula to this formula here, we see that the area of D is just the sum of these products, which you can write in this way. And this is kind of a beautiful formula because on the left-hand side you just have a notion, a concept, which is the area of D. But on the right-hand side, what you have is the coordinates of each vertices. So that just means that you can just compute the area of a polygon by knowing its coordinates. So you don't even need to know like what these edges look like and how they are like organized. You just need to know the coordinates of the vertices of these polygon, and that's a really powerful formula. So this is demonstrated in this example here. So we have this very irregular polygon here. And then we have those coordinates. So this is 1, 1. This is 12, 5. And this is 11, 8, and so on and so forth. So we have the coordinates of these vertices. And maybe in our middle school life, what we want to do is just to like split this polygon into a lot of triangles, and we know the formula for the area of triangle, and then we will do it in that way. But that's really annoying because you need to know all the length of the edges of these splitted triangles, and that's very troublesome, and I don't think it's kind of feasible here. But now, since we have this formula and we know the coordinates of these vertices, we can just apply this formula here. So, for example, for the first row, this is 1, 1, and this is 12, 5. So the mean of it is just 12 plus 1 over 2, which is 13 over 2. And the difference is, actually this is 12, 6, yeah. And then the difference is 6 minus 1, and this is 5. And then you can just multiply them together, and you get the product for the first edge. And then you can do the same for all the others, and then you can just take the sum of this column, and that gives you the area, which is 19. So this kind of shows the power of this formula and how Green theorem gives rise to that. So any question about the connection between the area and the and Green theorem? Yeah, I would also encourage. So this example is in Clark's lecture notes. I would also encourage everyone to try to verify all the other rows and see how it goes. Okay. And finally, the last topic I want to cover. So I said that I want to cover two significant applications. So the last application I want to cover is flux through a curve. So we have learned the flux across a surface. And this is basically the same idea, same intuition. So suppose we have a curve C, and it's oriented in some way, and it's simple, meaning that it's not intersecting itself. So we're also given a function f. So we know that given this curve C, it has some tangent unit vector at every point of C, and then we can just rotate it 90 degrees to obtain the unit normal of at that point of this curve at that point. So we have some velocity vector here, and then we rotate it 90 degrees to get the unit clockwise to get the unit normal n. So that gives us a vector n, and we have a function f, and the flux across this curve C is a line integral of the dot product between f and n along this curve. So what's the intuition here? The intuition here is that suppose f is a velocity vector of some field of fluid, then the flux is measuring the rate of fluid transported across C per unit time. So the green arrows are representing the velocity of the fluid. And then after integrating this dot product, what you get is the rate of velocity, like the rate of the fluid transported across the curve C. So how fast it is transported at every point here. And how fast, macroly or sum up together how fast it is in total, how fast is it transporting across this curve here, from here to here. Yeah, so that's the idea of flux across the curve, and that's the same as same idea as the flux across the surface. Any question about this definition or concept? Okay. And now we are discussing a lot about surface, about the region R2. So what we're interested here is that what if C is the boundary of the region D? So the curve is a boundary of some region D, of some region here. So imagine that we have a curve here, and so we have another region where the curve is bounding. And in this case, we can check that the unit normal is always pointing outwards from the surface. And from our intuition above, that's basically meaning that the flux is measuring the rate of fluid escaping from the surface. So you can imagine that the green arrow is escaping from the region D here. So the question is, in this case, we have this extra structure. The curve is the boundary of a region. How can we compute the flux smartly? And the idea is Green theorem. looks like my iPad is like stopped working.
Oh, really?
Yeah.
Oh, so
But-
that's not the connection?
Yeah.
Oh, wow.
But I think it's also like.
Yeah, well, that's
almost
true.
not-
It is pretty close to the, yeah, okay, so
Yeah.
you wanna, we can just go ahead and call it there if you can do that.
Yeah.
Okay, yeah. let's do that. Okay, thanks very much, Jason. I appreciate your coming in and helping out. Okay. Great. Okay, so y'all give me just a couple seconds to get my stuff together here. Also, I'm hoping I might be able to get a copy of that recording.
Yeah.
Possibly,
totally.
that'd be great. Thanks
Yeah,
very
sure.
much.